Hi everyone, and welcome to another episode of Mr. Carlson's Lab. In this video, together, we're going to repair and restore a Rogers Chairside radio, which is right behind me here. Now, when I went to pick up the radio, it really is quite deceiving. No matter how you take a picture of this thing, it just looks bigger in pictures than it is in reality. So I got to the place and I'm like, that's the radio? Which just added to the neat factor. The radio's so small, the entire cabinet and everything fits on the bench right behind me here. And I'll just move out of the way so you can take a look at it. So the cabinet's in great condition. The grill cloth looks great. Really hasn't been torn at by a cat or anything like that. On the top, there's a little door that allows access to the radio so you can put your coffee or your paper or something on that. Again, the thing is designed to sit by a chair. So what we're going to do is we're going to bring this thing back to life again. This thing is going to operate the way it did when it rolled off of the factory floor, maybe even just a little bit better because we're using modern components. So I'm going to take you through the entire restoration procedure with me step by step. So let's get started. Here's a closer look at the radio. If I open the lid up, you can see everything in here looks really, really nice. So the dial glass has no cracks. And that is kind of common for chairside radios, especially when the lids have been left open because the dial glass faces up. It's very easy for somebody to rest their hand on it or to drop something on it and it cracks the dial glass. So that's really nice to see that the dial glass is in good condition. The knobs are also in very good condition. These types of knobs decay when they're left in the sun or any type of UV light for any extended period of time. I have some very good examples of these knobs when they're just falling apart on some other radios that we are going to do some restorations on here in the future. So I'll show you what these things look like here down the road. They just absolutely decay. You can almost grab them and squeeze them and they just break into pieces. It's really bizarre. So you can tell that the top has been closed and everything's been nice and protected. As you can see, the grill cloth is in really nice condition. A bit of dirt down here I haven't cleaned off or anything yet. So all in all, the radio looks really, really nice. So on to the back side now. I'll turn the radio around and we'll get inside the thing, see what we're up against. Here you are sitting right beside me at the bench. So let's take the back off this thing and see what's inside. I can guarantee there's probably going to be a lot of dust. I can see lots of fuzz down in the bottom here. Definitely tell these screws have been out a time or two. I'm going to do my best to remain out of the shot. This is a very wide angle lens, so I'm going to have to stretch here a little bit. And I did notice that there was one larger Robertson over here. So I got a different screwdriver for that one. Let's leave that in there. The wire's out. And we're in. And yes, there is a lot of dust in the bottom. I'm going to have to vacuum that out. I don't want to inhale any of that. So it's looking really nice inside. What I'll do is I'll move the camera a little closer and we'll see what it takes to actually get the radio out of this thing. In order to get the radio out of the case here, it looks like there's a bunch of things that have to be done. First of all, I'll have to desolder the wires from the speaker here. So it looks like there is enough wire left here actually that I could just retrim it. It does look pretty rough down here. So what I'm going to do is I'll just cut that off right now. What I'll do in the end is just reconnect them. Right there and right there. So these are out of the way. I did remove the knobs from the top. Very easy process. One set screw in the actual knob itself right there. And the two upper knobs. So you just undo this set screw and they just pull directly off. There's really no rocket science to getting the knobs off on these radios. So both of them have a set screw. And then the portion that's underneath, this one here, it just pulls directly off. So they are indexed. So that one sits in the top. So you can't get the bottom ring out without removing that little screw there. You don't remove it, you just really loosen it off. And then this thing will just pop right off like so. Now looking at the underside here, I see a bunch of screws here. There's a nice vacuum tube legend here, which is kind of nice. There's 2 screws here holding the chassis in, and there's another 2 screws here. But I look up here, and I see that there's a filter here for the light. So to make the light shine uniform on the dial, but there's a needle that goes underneath here, and then as you move the dial, that needle moves back and forth under here. So if I was to try and remove this chassis without loosening this off, I might damage this, and it looks like somebody may have already done that. I see a little bit of a split here. So the thing to do, I can't get a screwdriver in here, but it looks like I can get a screwdriver in here. So what I'll do is I'll remove the dial string from this. You can see it's designed to be removed from here. And then I'll remove this screw and slide it forward, and that should allow me to get this needle out of here without causing any damage. So the first thing I'll do is I'll just loosen this off right now. So all you do is you pull the dial string forward. It's just kind of bent in here like so. And then in the end, I'll have to put this back on and align it again, which will be a bit of a pain, but you do what you gotta do. So there it is. Now this is loose, but you can see it's now hitting this. See how this is all loose? So let's see if I can get this out without... Nah, it doesn't look like it. So what I'm going to do is I'm going to undo this screw here and see if I can slide that filter forward just a little bit. Looks like it wants to pop right down, so this should be relatively easy. So if I move this all the way over here, hopefully I can get this forward enough that this will actually pop out. It feels like it wants to. You can see that there? Just like so. So that came out relatively easy without damaging anything here. So what I'll do is I'll put that screw back in here just so it holds this in place properly so that nothing really gets damaged. That back up in here. Just snug. Doesn't have to be tight. I also want to move this needle out of the way so I don't bump it and bend it or anything like that. So I'll put this over here on the other bench. Since the knobs have been removed, it doesn't really look like there's a whole lot more. So these 2 screws here and those 2 screws up there. And it looks like somebody's done the double-sized Robertson thing again there. Probably have to get a longer Robertson to fit in that one there. So I'll just grab this one here. So I guess... Okay. And I'll take one out down here as well. I'll get the difficult ones out. So I can imagine I'm most likely going to need to hold this up because it's going to want to fall. So what I'll do is I'll remove this one first, and then I'll go after this one here. I think this is the smaller one. Yeah, maybe it's 2 different size Robertsons here. So I'll just do this. And you can see it already wants to fall. See how I'm just holding it here? And there it is. So what I'll do now, it has a cover on the bottom, it feels. It does. So what I'll do is I'll just move this out of the way. Put this down here for now. So I'll get the cabinet out of the way, and I'll reposition the camera, and we'll take a closer look at the chassis, see what we're up against. I'm excited to see what's underneath that cover. So what do you think? Did the last repairman do a botchy job, or did he do an okay job? Place your bets now. Let's take a look at the chassis and see what the engineers at Rogers were thinking of when they put this thing together. Now, already I can tell you, they used a non-standard set of tubes in this All-American 5 design. Usually what they did way back when is they would have all octals or all 7-pin miniatures or whatever. They'd, have all of these types of tubes in here, which are called loctal tubes, and I'll explain the difference here in just a moment. but they're kind of have a mix of both of these, which is kind of odd, but maybe they were just trying to get rid of stock, or they were experimenting with some new tubes. The verdict's really out with that, but kind of an interesting design. We'll take a look at the bottom side here. So when I say octal tubes, they're much like 6L6s or 6V6s. It's a tube with an index pin. You can see a little index right here. See that index right there? That's so you can only put the tube in one way. Sometimes they don't fully populate all the pins. If the pins aren't needed in the base, they'll just leave them open like so. So in order to put one of these things back in, if you can't see it, what you do is you just put it on top of the socket and rotate the tube like so, and it'll fall in. See, like that? And then you just give it a bit of a push, and it's in the socket. Now, the question I get a lot is, can you touch the glass on vacuum tubes? Yes, you can. It's just standard glass. Nothing's going to happen to the glass. Now, you don't want to touch these when they're hot. This particular tube here is probably the tube that gets the hottest on this entire chassis. This is the audio output tube, and it's running in Class A, so this thing gets as hot as hell. And you don't want to be touching it with your finger, because if this tube was in service and you did that with your finger, you would have a burn on your finger. That's how hot this vacuum tube gets. It has a really large heater in there, and then of course when the tube is functioning and working and is drawing current, the entire tube gets extremely hot. This is a tube that you would not want to come in contact with. This one here would be the second hottest, and I would imagine the rest of them are, they get quite warm. So these two tubes here are doing a lot of work. This one here is taking the line cord and changing it to direct current. So this is a half-wave rectifier tube here, 35Z5. So I'll just pull this one out and show that to you. There it is, 35Z5. Dirty. Now, a lot of people get the temptation to take a radio like this and plug it in, just to see if it's going to work, see if it's going to hum or do whatever. Really bad idea if you don't know the state or you don't have a current limited supply, because the first tube that gets it is this one here. If the filter capacitors on the bottom portion of this chassis are shorted, and I'll show you what those look like here when we get into the bottom, if they're shorted, it immediately destroys this tube and you're buying another tube. So what it does is it blows the bonding wire off of the cathode. It's a little bonding wire that runs from the cathode to a pin. See if I can rub some of the dirt off here so we can take a look inside. So let's see if we can see the little bonding wire in there. There it is right there. You can see it running off to the side. So unfortunately it's under this getter compound. Let's see if I can get any closer. Yeah, you can see it. I'll get something to point to it. So right there, that little wire that's running off just like this. These white wires here are the filaments. And that little wire right there is what connects the cathode, which is that little pipe in the center. See that little pipe? That's the part that glows and that emits electrons, okay? So what it does is when that, you can see the little bonding wire in there. See it right there running down here, right? So that little bonding wire just blows off. It acts as a fuse. So a lot of people wonder why these radios don't have fuses. There it is. Overcurrent will just blow that thing right off. That's why these things were usually never fitted with fuses. Now, if you want to make it safer and for other reasons, you can add a fuse in here. There's no problem. But for the radio itself, that's instant destruction if you have a bad capacitor in here. So it's never a good idea to plug one of these things in if you don't know what state. Again, if a cap is shorted, you'll be replacing this tube right away. So this tube here changes the line cord right here from AC, because this is plugged into your AC outlet, changes it to direct current and powers up the radio. This is known as a transformerless type set. So a lot of the times the chassis on this radio can be hot. So whenever you're servicing something like this, you always have to have an isolation transformer to protect yourself. You can never ever work on this type of transformerless set without an isolation transformer, or you're really putting yourself at risk. If you have the line cord plugged in backwards and you attach a piece of test gear to this thing, you'll blow the line cord on this thing either open, or you'll blow the lead off your test gear or something like that. So it can be very scary. You got to be very careful with something like that. So if you're following along and you're working on one of these things, you're doing so at your own risk. You definitely want to know what you're doing before you're going to start working on a transformerless set. They are much more dangerous to work on in that respect than a chassis with a transformer. Chassis with transformers usually have elevated B+, so they have elevated high voltages, much higher than these. So, I guess you pick your poison, right? So that one's going to be a little bit, that's a different explanation. I'll get into that when we start working on transformer sets as well. So these tubes here, this one here is the mixer tube. So it's an oscillator and a mixer. This one here is the IF amp. So it's basically acting as an amplifier between these two IF transformers. This is a detector, which is basically a bunch of diodes, and a triode inside, which is acting as an audio amplifier for the audio output tube. The audio output tube here, which is a 50L6, drives this transformer. This transformer drives the speaker. Why do they need a transformer between this tube and the speaker? Well, vacuum tubes are high impedance devices, and speakers are low impedance devices. So we need something to transform that impedance. And that's what that thing does right there. Tuning capacitor right here. So one section will be the oscillator, and then one section will be tuning the antenna. So that's how these things work. That's why they have two sections. So both of these will have to be aligned. Same with this down here as well. Looks like it has a phono input on the jack on the back here. A phono jack on the back, if you want to say that. Look at this plating, definitely needs to be cleaned off. It's going all yellow. Not good to inhale any type of dust or anything from this. You got to be very, very careful. So these chassis are usually coated, and that's why they change color. So this is the bottom side, and it looks like somebody's been in here and they didn't put the screws back in here and here for some reason. Why, I don't know. Maybe they lost the screws or somebody was just asleep at the wheel. So it won't be too incredibly hard to get in this chassis. So what I'll do is I'll remove these screws. Again, what do you think? Hack job inside, or do you think it's going to be nice? I'm going to tell you the truth. About 90% of the time, when I hear somebody say that it's been repaired by a professional, it looks like something barfed under the chassis. I'd give it about a 10% chance that, you know, somebody with care, I guess you could say, worked on something like this. It's not really common. So I don't know. We'll see. Do you think it's the 90 or the 10%? Let's find out. Turn this thing upside down like so. Move this wire out of the way, and the big reveal. Well, you know, it's not doing too bad. It's all original. Lots of wax capacitors. All of these need to go. All the capacitors will be leaky. And he said it was repaired at some time. This one here's blown its end open. This is the reason that you really don't want to be plugging these things in before you know what's going on. This has actually blown the end off the cap here. I would think that maybe this capacitor here was replaced. That's about the shiniest one. So, yeah, that's probably the one that was replaced in here. It's usually the filter cap that goes, right? That, you know, when these things were first put together, run for a long period of time, these ones here were the first thing to go. So it's looking all original, you know, so there's not a whole lot of tampering. I really like that. So I'm going to say that the tech that put this in, there's a nice big shiny glob of solder here, so there was some testing, and that runs to this black wire right here. So that, I think it does. It looks like it. Yep. So this is most likely what they replaced here, and I have to say that the tech did a nice job. So this is that 10%. Congratulations to the guy that actually worked on this, because, you know, usually these things are taped up with black tape and thrown in the corner. You know, people don't clip them in like this. They don't put them under the clip again. Mind you, he did forget to put these screws back in, you know, so there's a bit of a discrepancy there. But other than that, you know, it's looking okay. This capacitor looks like it has a huge split in it as well. I don't know if you can see that. Big split there. There's a split in that one. This one here looks like it has its end blown open. We'll take a closer look at all this stuff here shortly. So all in all, like, I mean, it's not bad. Surprising. Very surprising. Now I was going to show you the Loctile tubes. Now, Loctiles have got an interesting way of removing. You're supposed to remove them in a certain way. See this little dimple on the side of a Loctile tube? The difference between a Loctile and an Octile is these ones will lock into a socket, so they're really good for mobile application. So for car radios and things like that. In order to release the lock, you bend the tube towards the dimple, and it should just pop out like so. That one really didn't make a popping noise, but they pop out. And you see how there's a little ring in the bottom here? That ring holds this tube in. So what you do is you align the tube up, okay, and then you give it a push. Hear how it clicks in? So you never want to rock these and pull them out. You always pull them towards the dimple. So you always have to find the dimple on the vacuum tube. So this one here has a dimple right here. So in order to get this one out, we want to pull that towards the dimple, and you can see how it releases the tube. And then to put it back in, you can align the dimple up to the same portion again to that little rivet, and then you just push it and it'll pop back in, like so. So that's the difference between a Loctal and an Octal. Technically, I'd honestly have to say that this is a better design than the Octal tubes. They used to have retainers on these things for mobile applications. So they had a spring type retainer. You'd push down on the spring retainer and then you'd pull the tube out. You see a lot of that in guitar amplifiers because their tubes are inverted, just like this thing. They're hanging upside down. And some of the guitar amplifiers, some of the really big ones, big speakers inside, when people are playing really loud, if they didn't have those retainer rings, the tubes would vibrate and fall right out. Whereas a tube like this would lock itself in place. You don't need the retainer. It's all kind of self-contained. So I don't know why these tubes weren't more widely used. I do believe that this is a better design. Mind you, if you take a look at this again, if you take a look at the pins, they're much smaller, right? Not a big deal, but as long as the pins, have got a good contact, this is technically a better design. So Zenith used a lot of these tubes. So there you go. So that's the difference between those. So getting onto the bottom side here, a lot of work has to be done in order to bring this thing back. Like all of these wax caps have got to go, and I'll test some of these things and I'll show you the difference between some of the ones that look okay. They look like this from the factory, aside from this, this is blown out to the side. So I'll show you the difference between some of these and some of the newer capacitors, and I'll show you the difference in leakage, and I'll explain a little bit about leakage and a little bit about ESR and capacitance and things like that. Capacitors have a lot of different tests. So the tests, you basically choose your tests wisely in a situation like this. We're not really so worried about ESR with stuff like this. We're worried about leakage and capacitance are the two biggest things that we're looking for. Now, these resistors here are known as roundies. What I could do is zoom in just a little bit. These are known as roundies. Now, these things here move in value a lot over time, just depending on their environment. This particular radio looks like it's been almost kept covered up over the years, so I really don't know how much these are going to move. If you test a bunch of the roundies and they're all really close to spec, there really is no point in changing them. If you test one or two of them and they're way out, you best go in there and just replace them all. The reason that the roundies, they move so much is that moisture ingression causes issues with these particular types of resistors. The newer Allen Bradley style ones have got a coating on the shell that doesn't really allow that moisture ingression to get in there, so they stay stable. And if you have Allen Bradley style resistors in your set, a lot of the times you can just leave them alone. So what I'm going to do here is, I don't think I've got one kicking around on the side. I'll just go grab an Allen Bradley one and show you the difference. Let's pull one out of my bin here. Something that's going to look, there we go. All right, so this is an Allen Bradley style, the newer style. Now you can see this one here has a shiny body on it. It's just me getting dust and dirt on it. They have a shiny body on them, and these things here usually stay very close to value. This is a 5% resistor, 47 ohms at 5%. And you can see these ones here, they've got kind of a gritty body on them, and they're all like that. Again, if they've been kept in a garage or a barn or something like that, a lot of times these resistance values move. So you got to go through and you have to test all of them. If just one of these resistors is out a lot, the radio's performance will suffer like crazy. So some of these resistors are very, very important. Some of these things are, running the plate supply to some of the tubes. If a resistor like this is out of tolerance a lot, there's going to be some issues. So you want to make sure that this here looks like it's a 33 ohm resistor. If the colors, this has been kind of hot. So what I'm going to do is I'm going to download a schematic here, and we'll take a look at the schematic and see what's going on. It looks like this might have an Allen Bradley. That looks like kind of an Allen Bradley style right there, actually covered up by that, covered up by this piece of coax here. They really did put the quality in here. A lot of these radios, what they did way back when is they just ran a wire over, and they'd rely on the bottom portion of the, the pan to shield it. They've actually used a shielded piece of wire from the front to the back. Rogers was always really good for that. That's a nice thing about Rogers radios is if you ever bought something that said Rogers on it, you knew that you got something that was fairly good quality. Same with Stromberg Carlson. Stromberg Carlson was also a very, very good quality radio way back when. They made some pretty fancy pieces of equipment. So I even have some Hammerland radios, some Hammerland communications receivers that are Stromberg Carlson Hammerland radios. So we're going to also restore some of those in the future as well. Lots and lots of stuff to do. So what I'm going to do now is start pulling out some of these capacitors. I'll show you how I take some of these capacitors out. I'll get all of those changed and we'll test some of the resistors together, get this thing ready to try out and align. This is my technique for removing components from a tube socket in a point-to-point scenario. I'll choose this one joint here. Just a random choice. There's a capacitor and a resistor soldered to this one area here. The very first thing I want to do is remove the tube from the socket. I don't want to apply any heat to this pin while the tube is in, and this is very important with Lochtel type tubes. So I'll pull this towards a dimple. You'll actually see this release here on the bottom. There it is. Reason being is because the actual pin on the tube goes directly into the glass on a Lochtel tube, and you really risk damaging the seal if you heat one pin up really hot, and it's kind of standalone, so you never want to do that. Always remove the tube. Now, with octal tubes, it's not that incredibly important. Reason being is because there's lead-out wires from the actual tube itself that run down into the pin, and then they solder the pin right at the end. You can see the solder at the end of the pins here. So if you were to heat the socket up a lot, you risk melting the solder and, maybe making the tube stick in its socket. But I've never had that issue. A lot of times I've worked on radios like this with the octal tubes still in their socket, this particular type of tube, with never an issue. And it doesn't hurt to remove the tube. So very important for these tubes, though, never ever solder with these things still in place. You really risk damaging the seal there. So in order to remove the components from this, what I want to do is I want to add some solder to remove the solder. So by adding some solder here, using my desoldering tool, which is this Heiko FR300 right here, it makes better thermal connection, and it also mixes with the old stuff and allows it to vacuum up easier. So this is a vacuum tool. So when I do this, it draws the solder in the end there and pulls it into this little chamber. And for those of you that own one of these tools, you're probably envious of this little red light on the end here. That is a definite needed thing. I do not know why Heiko did not put this in there. So it's very common to leave these tools on because their on indicator is right here. So that'll flash on and off, see, as it's heating and cooling. So when this thing is sitting in the stand, you don't see this, and it's very common to leave this tool on. So I added this so that I don't do that anymore. That's a nice little bright red LED there. I may show that mod here in the future. It's not a big deal to get one of these things apart. All right, so what I'm going to do is add some solder to remove some solder. So I'll add some here. As you can see, it's just sitting on top right now. So there you go. Now it's starting to take. And just vacuum that off, and you can see how quickly that took almost all the solder right off of that joint. See that right there? Right, cleaned that right off. So now, what I usually do after this is I'll go around and I'll look for how they've wrapped the component on there, and I'll clip a piece of the wire away, leaving enough to reattach the component that I want to leave on there. So this resistor starts here and it wraps around this way. So what I'm going to do is clip this off right over here. And this is always handy to have a really good sharp pair of clippers. Do that. I can just move this over like so. And this capacitor here is going to let go pretty soon. What I'll do is I'll just put this on the other side and peel this over this way, like so. And there it is. And you can see how nice and clean that tube connection is right there, right? Look at that. It looks like brand new. It looks like it's just been tinned. And that just comes with being careful. Now, a lot of people like to do the J-lead kind of thing. So what they'll do is they'll cut the old component off and they'll hook it over like this, and then they hook the new component onto it, and then they put a solder ball there. I've never liked that. I think that looks really messy. So to spend the extra time, trim away at the actual wire. So vacuum the solder off. And again, just clip away at the open portion, and you get a really nice clean result like this. You can put the new components in here. You can even use the little hole, put the components on, and it just looks like a really professional job, right? So nothing worse than, finishing off a radio and it looks really botchy, right? So that's one example there. You can try one more. Let's see, where's another one that'd be relatively easy to get into focus here. There's another one over here, so I'll try that one over there. So I'll move this around like so, and I'll add just a little bit of solder to this one as well. This is very important. Add a bit of solder, and then that way it's easier to make things happen, like so. And this one here looks, like it's wrapped around like so. So a lot of the times what I'll do is I'll even take this tool like so and just unwrap it once it's desoldered, like that. Look at that, how nice and clean that is. And it leaves a really clean result on the tube socket itself. And that way when you're working on something like this, when you're done, you're proud of your work. Everything is nice and clean. All the new capacitors will be soldered in nice and clean just like that. And I'll also take the time to locate the foil side, as I've mentioned in many of my other videos. And for those of you that are new here, I'll explain what that is here in just a little bit. So what I'm going to do is I'm going to get all of these capacitors out of here, and I'm going to start replacing these capacitors, and we'll start going through and testing some of these resistors, all that as well. I move this over like so. There is this split capacitor. So what we'll do is I'll remove this split capacitor. We'll open it up. We'll see how this thing is made. It looks like, this is 5,000 picofarad right there. See, 5,000 PF. So 5,000 picofarad is 0.005 microfarad. So the closest value to that would be 0.0047. So that would be the replacement. And it looks like it's just running up to the controller, either a tone controller or volume control at this point. So it shouldn't take too incredibly long to get this thing all done. And I'll show you my technique of installing new things as well as I'm going along here. So I'll get some more of these caps out and I'll be back. I've removed the tube from the socket over here, and I've desoldered this end of the capacitor from the tube socket. So what I'm going to do is remove this capacitor here carefully. I left a lot of lead on here so we can do some testing. Let's take a closer look at the failure point of this capacitor and try to understand what the capacitor meter is doing when it's reading this capacitor. And that will really help you understand what's going on inside the cap without even opening it up. So first of all, let's take a look at the ratings here. So the capacitor is rated at 0.01 microfarad. So there's nothing written here. That means 0.01 microfarad. It's common knowledge from way back when. DCWV means direct current working volts, and this is 600. So this capacitor is rated at 600 DC working volts. If you're to replace this capacitor, it's always okay to go higher in voltage. So you go with a 630, 700, 800, 900, 1000 volt capacitor. You never want to go lower than this. So you will not go to 550 or 5 or 400, something like that. You can always go higher, but not lower. The capacitance value you want to keep as close to the original value as possible, or you're going to change the operating characteristics of the radio. So it's going to either sound different or something will end up happening. They've chosen these values for a reason. You'll change the tonal quality, all sorts of different types of things. So you want to stay as close to this value as possible. And if you're ever working on an oscillator, this is extremely important to keep very, very close. Usually the oscillator ones are in the picofarads. And if you change those capacitors out, like the domino style capacitors or any type of a mica style capacitor that's in an oscillator, the radio will go way off frequency, and in some cases you won't even get the dial alignment correct anymore. So I'll cover more of that when we come across that in some future radios here. So we want to test this capacitor and see how close to 0.01 microfarad this reads, and then you can tell me whether you think this capacitor is still good or not with this one test. So what I'll do is I'll get my capacitor meter in here. It's a very nice capacitor meter. Fortunately, they discontinued this model a while back. I think they have the 260 now. But the 240 tests up to 200 henries, and that's the reason I went after this one. Again, I don't think this is in production anymore. The other one's very close if you're not worried about testing some extremely large inductors. Okay, so this is on 2 microfarad scale, and again, this is rated at 0.01 microfarad. So let's test this out, and let's put this off to the side. Well, it's reading 0.013, right on the verge of 0.014 microfarad. So do you think that this would be okay to use in circuits still? The capacitance very close, right? Well, why is this higher than this value here? Do you think the capacitor maybe is just an overachiever? Maybe you put a couple more turns in it or something like that? Well, how capacitor testers work, most capacitor testers like this, is what they do is they measure the amount of time it takes to charge this capacitor up, and then this does a math procedure inside to give us this value that we see on the display here. So if this is going to read high, that means that this is taking longer to charge. If this is taking longer to charge, it's going to look like a higher value, is what we're seeing here. So why is this taking longer to charge? So in order to figure that out, what I'm going to do is disconnect this here. And I'm going to grab another tester. So this tester here, let's turn this light off so there's a little less glare. So this tester here looks for a thing called leakage resistance. This is a DC test. This is not like an ESR test. An ESR test is an AC test. So this is just looking for leakage resistance inside this capacitor, okay? So what I'm going to do is turn this device on, and we're going to see if it's going to leak internally. Now, when I say leak, I'm talking electrically. I'll explain that here in just a moment. I'll just attach this like this. Any old way is just fine. And I'll put this on to test. Now, if these LEDs come down to here in this little lamp here, the LED in here switches to green, that would mean that this is okay. And the amount of time it takes to do that is very important as well. You know, if you wait a day and a half and it slowly starts to climb down, that doesn't count. So I'll show you how this compares to a brand new capacitor in just a moment. So as you can see, there's no movement. The thing's just on red. Nothing's happening, right? Again, this thing here is a low voltage leakage tester. So this thing is using low voltage to test this thing for excessive leakage resistance inside. Okay, so as we can see, there really is no change. So I'll just disconnect this like so, leave the leads open. So what I'll do is I'll take a brand new capacitor here. So this is the same value, 0.01 microfarad. This is rated at 630 volts. All right, so this is the modern replacement for that, okay? What I'm going to do is put this in here just like so, and watch what happens. Look at that, how fast that changed. There's almost no leakage resistance in here. Very, very, very little leakage resistance. So if I do this, I'll shut it off again, okay, and discharge it, and I'll try one more time. Here we go. Look at how fast that works. Comes right down. Again, the old capacitor, shut this off, do the same test again, put this in here like so, and like so. Okay. And here we go. And as you can see, there's virtually no movement there at all. So now that we know this, we know that this thing has excessive leakage. So this thing is looking like a resistor. So if you were to take a high value resistor and bridge it across this capacitor, that's what this is starting to look like inside. It's now a resistor capacitor, I guess you could say. So there is parallel resistance being formed by the decay inside this capacitor, and that will form a thing called leakage resistance. As this decays, that leakage resistance will end up getting closer and closer and closer to being a dead short. Okay, so I'll just disconnect that, shut the device off. So now, again, I'll get the other capacitor tester out here. So here we go. So now, again, if we look at this here, let's hook this up to the cap tester. There we go. 0.013 microfarad. Now, as I explained earlier, if this takes longer to charge, this is looking like it has more capacitance, right? Because it's, it's displaying more capacitance here. If it takes longer to charge, the reason it's taking longer to charge is because there's a resistor formed across this inside. You can look at that as almost like a make-believe resistor being formed across here inside. If there's a resistor across this capacitor, it's going to take longer to charge this capacitor, right? Because there's leakage across it. And that's what this is showing. That's why the capacitor meter reads high. So for all of you that think when you're working on an old radio, if you just use a capacitor meter like this or any other type of DMM style capacitor meter and you test the cap like this, you look on your meter and it reads a little bit high, you're thinking to yourself, oh, it's just an overachiever, it's a really good component. Well, no, the reason it's reading high is because it's failing. So here we go. Brand new capacitor. 0.01 microfarad, 630 volts, the same one that we just tested. Let's see what it reads on here. Spot on 0.01. That's how it should read. So there is an explanation of what's going on in those capacitors. Now, there's a lot of other tests for capacitors, and I will cover more of this in the future. I've talked a lot about this stuff on Patreon. Those capacitor testers, I have another capacitor tester as well, which will also indicate the outside foil. And there's another really interesting thing about this circuit, and I'll explain that in just a moment. So that capacitor tester that I just showed you right here, this one, I'll just remove the leads so that way they're not hanging around. This little tester that you see right here is on Patreon. All the plans to build this and the schematics, the instructions, the alignment procedure, all the measurements, to drill the box even, everything is available up there. Lots of people have made these things and they're extremely happy with the result. Just lately, there's a few people that have put some stenciling on these boxes. I haven't had time to do that with this yet. But there's a lot of people that have put stenciling on these boxes and they look just incredibly good. They've done some really nice work putting these things together. So this is up there. So if you're interested, if you're a guitar amplifier repair guy, or if you're working on switch mode power supplies that have lots of poly style capacitors, snubbing networks, things like that, if you work on old televisions, radios, communications receivers, this thing is indispensable. I use this thing all the time, and it even has a forecast setting, which will, the minor amount of leakage resistance that this capacitor had is a major amount of leakage resistance in this position. This will look for the absolute teeniest amount of resistance being, a leakage problem in mica capacitors and things like that, ceramics and all sorts of things. Extremely sensitive, low voltage capacitor leakage tester. This thing works incredibly well. And again, I've shared this with the entire community on Patreon. So if you're interested in putting something like that together, and you are one of these guys that repairs things all the time, or if you're just a test equipment buff that likes to have very accurate readings, know what's going on inside of things, this is definitely a beneficial thing to have on your bench. For those of you that were really paying attention in the last shot, you may have noticed that before I had this capacitor fully attached to the tester, you saw the little LEDs flicker on the meter here. Why did that happen? And that also brings up a very important safety topic when using test leads. Well, first of all, this device is so incredibly sensitive that it will see my body's resistance through these boots. I'm not even contacting anything metal. So to give you an example, I'll just pinch both of these boots and look what happens. I'm not touching any metal, I'm just pinching the boots. And that's the reason it saw that. Now, if I make contact to the supply, it's even more sensitive because now I've got the supply on me from this device here, and I can just gently hold this and it'll go right to the top. And that's extremely sensitive in the forecast setting. You know, I barely have to hold these things at all. As you can see, it just goes right to the top. So that's the reason you saw the meter move. So what does that tell us? Well, if it's seeing my body resistance through these things, are these things really acting as insulators? Not really. They're resistive. Very important thing to remember if you're ever working on any type of high voltage gear and you have test leads, never ever rely on the boot to protect you if there's a supply on in the device. Never pinch this. What you're doing is you're grabbing the boot, and as you squeeze this tighter and tighter, the resistance is going down. If there's even the slightest hole in one of these boots, and this is attached to something in circuit, and you go to unclip this while it's live, you could receive an extremely bad shock. So always remember that. Not all test leads and alligator clips are created the same. These boots here are conductive. Let's see if this one here is. I'll just clip this onto this lead right here, put that over here. It's on forecast, so what I'll do is I'll just grab the boot of this and the boot of this. See that? Look at that, it's conductive. Look at that, right down here even. The wire itself even looks like it's mildly conductive. I just hold this over here. Look at how conductive that is. I'm not even close to the top. So there you go. You can also use this device to see how incredibly conductive your test leads are. So again, can you imagine if there was, a couple hundred volts on this or something like that, and you forgot to discharge your device or turn it off, and you went to grab this and you pinched it? Something to be very, very aware of. So just be careful. Make sure all of your devices are discharged and everything is unplugged, and all the voltage is gone out of your equipment before you go about grabbing one of these things and pinching them to remove them. As I'm going through this radio receiver, replacing all of these older capacitors, I want to make sure that I'm installing the new capacitors the exact same way I'm removing these old capacitors. What do I mean by that? Well, you'll notice on this capacitor here that there's a black band that says outside foil. What does that mean? That means that this lead right here is attached to the outermost foil layer on this capacitor. That outermost foil layer can be used as a shield for what's inside. So you can picture the outermost foil layer like the braid on a piece of coax covering the entire capacitor and being attached to this lead right here. Now, you can see where this would be important in a vacuum tube circuit. Vacuum tube circuits are very high impedance circuits, and these things are usually elevated above the chassis. There's lines running below them. So if this was attached to, say, the screen grid of a tube, and this was acting as a bypass capacitor, this end would be attached to the chassis. So this entire capacitor would be shielded right up to this point right here, and only the lead that's exposed to the actual tube socket itself would act as somewhat of a interference pickup or a hum pickup. If you were to reverse this capacitor and tie this end to the chassis, this whole area of the capacitor is now attached to the grid of that tube. So if you had a filament line running underneath this thing that had, quite a bit of current on it or something like that, what'll happen is that filament line could interfere with this capacitor. So this capacitor could pick this thing up like a hum antenna. And I'm going to explain what a hum antenna here is in just a moment. So it's very important to make sure when you put your capacitors into circuit that they are orientated the correct way. There's a reason they put this band on the capacitor and put outside foil on all these older capacitors. These capacitors are in high impedance circuits, whereas all of the modern circuitry, the majority of modern circuitry, is a lot lower impedance than this stuff. And that's why on a brand new capacitor like this, you don't see any markings. So they don't tell you the outside foil. Usually with a capacitor like this, it's sitting flush on a ground plane on a circuit board, and the leads are bent down, so it's shielded right there alone just by having this thing on a ground plane. And then of course you have a box around it. Most of the circuitry that surrounds these capacitors nowadays is DC, whereas in an old radio receiver like this there are a lot of AC lines running around. You have the filament lines running around which have current on them and they're carrying AC. There are so many reasons to put these capacitors in circuit the correct way, and it really does affect the performance of many receivers. Now, a lot of techs think that it's not all that incredibly important. I can just put this thing in any way. Well, the outcome is only as good as the work that you put into it, right? And I've had receivers that have come here that are breaking into oscillation when people have recapped them, and it's due to a capacitor that's put the wrong way. You just change the capacitor around and the oscillation stops. So in very sensitive circuitry, this is all important, and I can't stress this enough. So if you're working on guitar amplifiers or radio receivers, televisions, anything like that, spend the extra time and just locate the outside foil and do yourself a favor. Tuck the capacitor if it needs to be close to the chassis as well. The lead length from this end to the tube socket should be as short as possible. If you need to add a heat relief, put a small coil in to the actual tube socket itself. There are many things that you can do. Take the extra time to locate that outside foil. Do the best job you can. Now, in order to locate the outside foil in this, there's a lot of ways of doing this. You can take, the leads from an amplifier and hook it both ways and listen for the hum. I've created a box that just makes this a whole lot easier. I've created a bunch of devices. One of them I show here right on YouTube, and this was the latest one that's up on Patreon here. And this one here just automatically locates it. So very simply, all we're doing is we're looking for the lowest amount of LEDs with the corresponding LED lit down here, and that tells us the outside foil layer. So let me give you an example, okay? So I'll just put this in here like so, and I'll put this in here like so, okay? So it's just clipped in the leads just like this, and I'm just going to hold this with my hands. I'm acting as the hum antenna. Something like an open AC line under an incorrectly placed capacitor would act like, okay? So I'm just going to hold on to this, and I'm going to turn the device on, and we'll look for the LED with the lowest LEDs. So you can see this LED is lit with the lowest LEDs up here. When I touch the box, I ground myself out. See that? The lowest amount of LEDs with the corresponding LED down here indicates the outside foil. So this side here is the outside foil. Just that simple. So what do? I remove this like so, get my pen, put a little black dot right here so it doesn't deface the capacitor, just like so, and now that's the outside foil end. So this capacitor, let's get this out of the way, so this capacitor would be in circuit like this. I would know to take this end and put it this way just like this. Outside foil on this end, outside foil on this end. And now this capacitor is put into circuit the right way. Now you might be thinking to yourself, well, is all the writing like this on all the capacitors? No, they're not. These things are going down the production line every single way. This way, this way, this way. They're going all down the line in different, I can sort lots of these things and get about a 50-50 mix, it seems almost. So 50% of the dots will be on this side and 50% of the dots will be on this side. I've sorted lots and lots of these capacitors. These are excellent capacitors, by the way. So it's very important to locate that. So yeah, you got to take the time to grade all the capacitors that go in, but if you create a device like this, it just goes that fast. So again, this is available with all the plans and everything up on Patreon if you're interested in building one of these things. Very handy unit to have. Makes life a lot simpler. There is a lot of mileage on that box, I can tell you that. That thing has switched back and forth many, many times. So I'm going to start installing all these capacitors into the chassis, and when I have all of those caps in there, we'll look at the resistors. And through the magic of the camera, 3 days later, this is the point I'm at on the underside of this chassis. Some of you might be asking yourself, well, it doesn't look like a whole lot of work has been done here, when in fact a lot of work has been done. And I'll explain my entire thought process as I've changed these components and changed some of the components completely to a different style, and as I've done all sorts of things. You'll notice that I've left all the resistors behind, and that's because we are going to test those resistors together. So what we're going to do is we'll test them all. We'll see if we should replace every resistor in here. Should we only replace the ones that need to be replaced, or can we just leave them all behind? And I'll explain my thought process in that as well. Again, these resistors are very susceptible to the environment that they've been kept in over the years. Again, when we test the resistors, we'll get back into that. So one of the very first things I always like to look at in a chassis like this when I'm working on it is I like to think about the safety factor. How can I improve the safety of this radio receiver? One of the very first things to do is get rid of that line cord that isn't polarized and put a polarized line cord on. So grab the non-polarized line cord that's behind me here. This is the one that came with it. You'll notice that you can plug it in this way or you can plug it in this way. Either way, there's no polarization here. There's no indexed pin. Whereas on the replacement line cord, there is an indexed pin. You can see this, so we can only plug this in one way. That allows us to keep the neutral side of the AC line as close to the chassis as possible, whereas with the other line cord, we have a 50-50 chance of putting the chassis closer to the hot side, and we definitely don't want that. Now, it's not as simple as just changing a line cord. A lot of the times they put the switch in what could be the neutral side, so that has to be all changed. What I mean here is, this is the factory schematic right here. So you see this is the line cord here, this is the plug, and you'll see a switch, and that switch runs over to what would be the ground of the radio or the chassis here. You can see how they've tied the chassis through a capacitor. They've AC coupled the chassis to the ground here. So if you were to plug this thing in, you have a chance of putting the switch in the hot side, all right, but then the chassis of the radio is close to the hot side because of this capacitor. The other catch-22 is if you flip it around, now this side is hot, but this side is neutral. So now you've put the switch in the neutral line. So if you open that switch, the hot side is still connected all over here, so there's a really big chance that the chassis itself, through all the other components, is going to be led to the hot side. It'll be AC coupled. So any way you look at it, if you leave this switch on this side, it's still kind of a dangerous thing. So you have to remove the switch from this side, make that a solid line, and put the switch on this side here so you can only break the hot connection. And the neutral side then is now firmly attached to the chassis. And then of course we have our coupling here, AC coupling through this capacitor to the chassis. Now C24 is often known as the death capacitor, kind of strong words for a capacitor. But what happens is these capacitors, they end up shorting out, and what they do is if you have this plugged in the wrong way, say this is the hot side and the switch is closed, it attaches the chassis directly to the wall outlet. Kind of a scary situation. So that's why we replace all those capacitors with X1, Y2 rated safety capacitors all over the place here. Now you're probably saying to yourself, "What? How come there's only one here, right?" So there's only one. How come there's so many of these capacitors? Well, this is something that a lot of techs overlook. They have to be put in more places than just there because there's external connections all over the place here. So, for example, okay, we have a capacitor here that's across the line. All right, so we need one of those capacitors there. That's this capacitor here. This capacitor here is a higher rating, so this capacitor that runs from the chassis to ground also needs to be one of those style capacitors. Now, because this has got a higher rating, I use two of them here. So there's two X1, Y2 rated capacitors from the line to the chassis right here. So that just gives me a little bit more capacitance, that's all. Now, what about these ones? Why are these ones over here? Well, if we go all the way over to the antenna connection here, this is one of the wires that leads out of the back of the radio for you to attach an external antenna. So we can see it goes through a coil here, and then look what's here, a capacitor directly to the ground again. So in order to isolate this connection, we need to make this a safety cap as well. And if we go to the external ground lead, there's a cap in line with it as well. Remember, this is to AC couple. We're dealing with RF here, right? I mean, this is not a DC situation. So this is the reason that capacitors are acting as isolation here. So you can see that we have a capacitor on the hot side, or the antenna side. It's actually on the ground side of the coil. You can see that here, or on the neutral side of the coil. And then it says here external ground. We can see the actual external ground connection is here. So this allows us to isolate the radio, and also if there was to ever be a problem, like say there was a connection, that would create any type of current on this side, say the wiring in your house was reversed or something like that, right? So say which is kind of common, but say the wiring was reversed. If the hot side was on the chassis here, this is just extra protection, because this is going to really lower the amount of current that can be passed here. It's going to pass current, but it'll be very low through these two values. So these need to be safety caps as well. And of course, capacitors isolate DC completely. So if you're to ever come across this with some form of a DC source, nothing would happen to the coil. And the capacitors are low enough in value that, if something was to happen, it wouldn't fry this coil. If there was no capacitor here on, say there was no C2 here, and this end went directly to the chassis, if for some reason this was plugged into the hot side, okay, so if this was switching the hot side and the hot side was here, the hot side of your AC line would go right through this antenna coil, right to that connection, to the antenna connection on the back side of the radio. So, any type of connection to that would blow this coil sky high. It would be a huge flash inside the radio, and it would be done. So, very important to have safety capacitors right there as well. And that's the reason that they're all over the place here. So you can see them here. Now, the line cord itself had a knot tied in it, just like this. A lot of people ask me, where do you get your replacement line cords? This line cord is just a 6-foot extension cord, a very good quality 6-foot extension cord. Another thing to be very leery about when you're buying a cord to use for something like this, it needs to be a high quality cord. There's a lot of garbage on the market nowadays. Another thing, when you're tying the knot, make sure that the wires don't overlap. They like to twist and overlap. You want to make sure that the wires go through the knot perfectly. Now, the knot itself, you'll notice this is a strain relief, so I can't pull the cord out of the radio. And there's also slack in the wires so that nothing gets tight on the terminal tie strips. You'll notice that this knot here is right up against the chassis. And if I turn the knot, if I try to turn the knot, you can see that it's not going to really hit anything except the actual chassis itself. Now, you'll notice that if I find it over here, lots of rubble around this radio because I'm replacing so many components. You'll notice that there's a terminal tie strip. Now that's right here. This is a terminal tie strip right here. All right, so this is where you use to tie off external components to. If you're doing point-to-point wiring, you tie it to here and you can run things around. That's why these things are here. These sometimes are called, tie boards or whatever, but most commonly known as a terminal tie point, terminal tie strip. Now, we don't want that knot to come touching this at all, right? So that's very important. Now, there's a bit of a thought process in that as well. First of all, you got to make sure the knot is tight and that the wires aren't overlapping, or your knot will become very big and then it'll rub things. You don't want anything to rub the line cord because the line cord needs to be protected from all that. You'll notice that there is a slight chance of this wire, since there's a big droop here. You can't really see it on camera because we're looking straight down, but there's quite a bit of a droop here as it goes to this terminal tie strip. You'll notice that there's a droop here, and there's a chance that it could come close to this terminal here. So there's a piece of high heat shielded tubing here. This is much like the stuff that you find in your toaster oven, and it protects the cord here. So if anything was to ever happen, it would rub against this. This is silicone coated as well. Very, very high heat stuff. Very important to have. You'll notice that there's also a loop here acting as a strain relief on the other portion, and you'll notice that there's a zap strap or a tie strap down here. So that's holding this wire steady and keeping it away from components, as you can see. So the strain relief is working. Now, I could tie a knot on the outside as well. Not really too needed in a case like this, and in many radios there is no knot on the outside. If you're concerned about pushing the cord back into the radio, which is really kind of hard, you could put a zap strap or something on here as well. Now, this here is kind of a different scenario because this is hiding up inside of a wood cabinet, and there's, maybe a couple of feet down to the bottom, 1.5 feet, 2 feet down to the bottom of the cabinet where it runs out of a little cutout on the back side of the radio. So there's really no twisting up here, and there's so much line cord that, you could move it around down here and nothing happens up here at all, right? So this is running over here through the zap strap, which is holding this out of the way, and then that runs over here to where the line cord joins together again. You can see that the line cord is joined here. There's a little bit of a trick in doing that. And the line cord itself is pressed flat against the chassis as it runs all the way along here. This is very important to keep the flat side of the line cord running against the chassis because you want this kept away from any signal carrying leads. You want this as far away from the audio. This is way up on the chassis. This here, again, we're looking down, so it's kind of hard to see. This is way down at the bottom of the chassis, and it's away from any signal carrying leads or anything that would be sensitive to picking up hum. In a lot of cases, it's a good idea to also twist the line cord tightly and run it up here. Since this is still a piece of line cord that's one solid piece and it's close to the edge of the chassis here, it's absolutely fine to leave it like that. So when I'm putting the line cord in, what I do is I pull about, 1.5 feet of it through and then tie the knot. So I've got about 1.5 feet here and I got a lot of stuff to work with. So the 1.5 feet that's beyond the knot here, what I'll do is I'll say this is in the radio here, right? So say this is coming through the radio like this. I'll figure out how much I need to go from here to here, and then I'll clip the appropriate lead and then just move them out. And then I'll leave this together, and then what happens is it joins back up here again and I get a nice solid piece. So it makes for a very clean install with the line cord. So this is all still together here. And of course that eliminates another connection as well. Now the original line cord had a knot in here, and this looped right underneath this oscillator coil and came all the way back. That's a huge no-no in design, and that was factory, something that the person who assembled this radio should have known. So the oscillator portion of the radio is very sensitive to any kind of movement. It's also sensitive to any type of thermal movement. So as we all know, tube radios go from being dead cold like this to as hot as the blazes of hell when they're working, right? So we need to make sure that the components and everything that's around the oscillator section is very solid and won't thermally move. Now, having a line cord that can just move around with it drooped under the line cord by me moving the line cord or just moving it will cause frequency drift on the dial because it's going to move closer and further away from this coil. This coil is very sensitive to anything that's placed close to it. If I'm listening to a frequency and I move my hand close to this coil, the thing will go right off frequency. That's how sensitive this is, a big air core coil over here. Now, what they've also done factory to save money is they used wax capacitors to couple from the oscillator coil into the circuitry over here. Now they took great care with the tuning circuitry over here. This is a ceramic style capacitor with a temperature compensated capacitor across it. But what they used to couple it into the circuitry over here was wax, which doesn't make any sense. So instead of, replacing that with just a standard poly style capacitor, which many people would probably do, you want to use the most thermally stable components in a section like this as possible. So you want to use like a mica capacitor or an NP0 style capacitor. So these are micas at the same value of the waxies that I put out, and I've replaced all 3 of the waxies that are in the oscillator section here with micas. So that'll greatly improve the stability performance of this radio receiver. I bet you way back when you tuned this to your favorite channel or to your favorite frequency on the AM dial, if you listened to it for 15 minutes, it would zip off frequency in 15 minutes and you'd have to correct it. This should compensate for that, and that would no longer happen. Again, these capacitors are expensive back in the day, and they still are kind of expensive mica capacitors. So there's no bean counters here, right? And I'm rebuilding this thing. I want this to be as solid as possible and as safe as possible. So why not use the best parts as possible? Just make the thing better, right? Now, you'll notice that I've left all the resistors in, as I said earlier, and we're going to test all of these things together. I've also left this capacitor, and I didn't change this one. This is a ceramic tubular style capacitor, and they very rarely fail, and this is a critical component. If you change this out with just a standard, ceramic non-NP0 style capacitor, that will incur frequency drift with temperature change. The reason that they use these ceramic capacitors is they're very stable with temperature change, and that's the reason it's across this adjustment here. This is a very sensitive adjustment. This is what's going to allow us to align the band later. So this can be left in circuit. These very rarely fail. And in fact, a lot of mica capacitors can be left in circuit without having to change them if they're still okay. Now, again, if the radio's been exposed to a bad environment, say it's been in a garage for 30 years, or say it's been in an attic or something that hasn't been temperature controlled, you'd probably want to check the micas just to be sure. Now, again, a lot of the capacitor leakage testers, the high voltage ones, won't see the leakage in a mica capacitor, especially if it's starting to get just slightly leaky, whereas that capacitor tester that I've shown you earlier will see the leakage in all of these, even if it's the most minute amount, and that'll give you an idea of what environment it's been, kept in. So something to keep in mind. So not all capacitor testers are created equally. So the device that I've created, I'm a test equipment aficionado, and if I find something that needs to be tested in a different way and there isn't a device out there to do it, I'll just make it. And that's what I've done. And again, I've shared that on Patreon with everybody. There's a lot of test equipment that I've designed and shared up there. So now all the other wax capacitors I've replaced with these and these orange dip style capacitors. These black dots here indicate the outside foil end. Since this is ground, this is the outside foil end of this capacitor. They're very close together. They will not couple because this capacitor is shielded from this one here by its outside foil. So I can therefore put these very close together and keep them away from the line cord. Another perk of locating the outside foil. These capacitors all have the outside foil end located, and these have all been installed in the circuit the way they should be. You'll notice that the ground end of things is longer, and the capacitor itself is placed closer to the tube socket to reduce lead length on this side. So this capacitor is shielded right up to this point right here, and this is the only little bit of lead that's exposed. And it's the same way with all the capacitors that need to be done like that. So they're all placed into circuit this way. The ones that are very important, you'll see the long lead length here is very long lead. This actually runs down to the tube socket. It's up off the tube. You can see that there. See how long those are? And there's very short amount of lead. And again, this is running to common. Okay. So where did my capacitor? See, I'm using this capacitor to hold the radio up, and it's stuck to the dial now, which is a good thing. So there we go. What else can I tell you? The filter capacitors have been replaced. This filter capacitor here is the original. Now, this isn't original to the radio. This was a replacement that somebody had added in here. The capacitance values are too low. It's supposed to be 80 and 40. This is 50 and 30. And we can also see a price of $2.25 way back in the day. So this thing is out of there, and it's been replaced with two very I guess you could say high quality Rubicon capacitors. And these are also rated at 105 degrees C. Capacitor technology's come a long way since way back when. One thing to keep in mind, another hint for any of you that are just getting into this, these capacitors here are counterfeit all over the place. You got to be very careful. If you want genuine components, you got to go to a reputable source. It's very easy to purchase counterfeit capacitors now. So these are genuine Rubicon components. There's a lot of things that you can tell. The counterfeiters are getting kind of tricky. They're even starting to use the same vent stamp. But the vent stamp is one way to tell if it's a counterfeit capacitor. Look at the writing. Compared to a new device. If you have genuine devices, you can compare them. The bottom, you can compare the heat shrink, the actual tubing that they use. There's a lot of things to compare. But they are getting pretty tricky nowadays, so you want to make sure that you're getting genuine parts. Now, these parts here are held by these standoffs. I had to add the standoffs because this was clamped to the front, right, with this clamp right here. So I added those standoffs, you can see, and those hold the capacitors in place. Now, and they're also the electrical connection. Now, the big thing with this is, if this was in a guitar amplifier, so say you're working on a guitar amplifier, it has two 12-inch speakers, there's a bunch of 6L6s or EL34s or something underneath it, and you were to replace these capacitors, you can see that they're just loose here. You'd want to put some silicone underneath these capacitors to hold them so that they're not going to vibrate, because if they're in a high vibration atmosphere, you don't want this thing buzzing against the chassis. And of course, that's going to create external noise. You don't want that, and it's not good for the component. This is not in a high vibration atmosphere, so it's completely fine to leave these like this. If you're going to fasten capacitors or anything down in a chassis like this, don't use normal silicone, and don't use hot glue, because these things get very hot. The hot glue will just let go. What you want to do is use a product called GE Silicone 2. Now, I'm not endorsed by these people at all or anything. It's just a really good product, and it won't corrode the area. It's a very non-acidic type of of silicone, it doesn't have that vinegary smell. It has a very mild smell to it, and it won't corrode the area. That's the kind of stuff that you want to use. All right, I usually buy the big caulking tube and put it in a caulking gun and use it to fasten things if I need to do that, if they're in a high vibration atmosphere. Things that you need to definitely think about. Not only that, if this is in a high vibration atmosphere and this thing is moving like this a lot, what it's going to do to the solder joints over time, right? It's going to try and open them up. So you got to be very careful with that. So whenever anything is in a high vibration atmosphere, you always want to make sure that it's attached to a chassis very firmly with something to hold it so that it'll dampen the vibration. What else can I tell you about this here? So much has been done in this chassis. I haven't cleaned the VRs yet. I'm going to use some contact cleaner to clean the VRs and this as well. The oscillator coil here, because the line cord was moving in there and stuff, this here came loose, so I fastened it back into the bottom here. New wires run from the standoffs to the same location that the factory capacitor was installed. There are some other capacitors here as well. These ones here I removed. We're going to test these and see what's inside these things. They look very much like a mica capacitor. And what we're going to do is test these with that cap tester, and without even opening this thing up, let's determine what's going on inside this thing. I replaced those anyways. I just replaced all of the bulk capacitors in here just to make things more dependable. So I still need to clean the upper side of the chassis and get this thing ready for alignment, all that kind of stuff. So the next thing that we're going to do now is we're going to go through and test all the resistors, and we'll make a decision as to whether those resistors need to be changed or whether we can leave them behind. Again, I've put all the tubes back in circuit to give you a demonstration that the resistors can be tested in circuit in vacuum tube circuits, because tubes are high impedance devices, unlike transistors and everything else that'll be, mounted to a circuit board. A lot of the times on circuit boards, the components around the resistors will skew your readings because you're dealing with a lot of lower impedance devices. So vacuum tube equipment makes testing these components a lot easier because the tubes look like an open circuit most of the time, right? So I'll get the meter all set up and I'll be right back. All right, let's test some resistors together. So what do you think? Do you think they're going to be relatively close to their value? Do you think they're going to all be way off? Well, let's find out. So I've left all the vacuum tubes in circuit as mentioned before, and we'll test all of these resistors just the way they are. The only one resistor that I've removed one end on is this one right here, and that's because it's across two variable resistors, and there's bound to be some hiding parallel resistance in there that's going to give us a funny reading. So just to be on the safe side, I just desoldered one end. So if you ever know that there's some hiding parallel resistance somewhere, it's always a good idea to open one end of the device or get rid of the parallel resistance so that you can get a nice solid reading on the device in question. Another thing you'll notice is all of these resistors have a silver band on them. That silver band means that when the resistors came from the factory, they were within 10% of their reading. So whatever they say on the top of the resistor in their color code, it's within 10% of that. This radio was produced in 1947, and if it's moved just a little bit beyond that 10%, chances are it's going to be pretty stable by now, and it's not going to move any further. So if it's moved slightly beyond in either direction, I'm not really too concerned about it. It's not going to affect the performance of the radio receiver. We're not dealing with precision voltage dividers here or anything like that. If they've moved a long ways, yeah, of course, then we're going to end up replacing resistors in this thing and making sure that it's going to work properly. As I go through my videos here in the future, you'll get a better feel for which resistors can stay in circuit and which ones should actually go. We're going to be working on a lot of test equipment. We're going to be working on radios and televisions. I haven't done a television yet, but I've got quite a few of them here. So we're going to go through all of this kind of stuff, and you'll get a better feel for which resistors can kind of hang out in the circuit and which not going to make much of a big deal whatsoever. So as I'm going along, I'll tell you which resistors are good and which ones, need to go. So I'll just choose a random resistor here and I'll start with it. So I'll start with this one here. So we always want to read towards the silver line in this little gap on the end of the body. I'll use one of my probes here as a pointer. I'm using this meter right here because it has a nice big display and it reads relatively fast. It's the only reason I have this in the shot right now. So let's take a look at this one here. So it's yellow, purple, yellow, silver. So yellow is 4, purple is 7, yellow is 4, and then this is the 10% band. So 474 would be the code for this resistor if it was a modern device. If it was on a circuit board, on a modern surface mount type resistor, this would say 474 on the top of it. It's just these older resistors, they read in colors. So the trick to making this really quick is knowing the first two colors, 4, 7, and then the next one is the multiplier. So you change that number directly into zeros. So if this is the number 4, use 4 zeros in that spot. All right, if we look at this resistor and we see it's brown, we know that's the number 1, so that's 1 0. We see red over here, that's the number 2, so that's 2 zeros. So 4, 7, and then 4 zeros is 470,000 ohms or 470 k ohms. So let's see how close this is to that value. I would say that's pretty close. No problems with that resistor. So far, we're doing very good. This one here is orange, white, yellow. So orange is 3, white is 9, yellow again is a multiplier, so that's 4 zeros. 390,000 ohms or 390 k ohms. So let's see what this one reads. That one's way off, 493 k ohms. So it's 390 and it's up to 490. So it's 100 k ohms off. So this one here definitely has to go. So one bad one. So far it's 50-50. Let's look at this one here. Red, red, orange. 2, 2, 3. So 2, 2, and then 3 zeros. 22,000 ohms. So let's see what this reads. So it should say 22K or somewhere around there. 22.6, 22.7K. No problems. That can stay in circuit. So 2 good ones so far. Let's test this one here. Green, blue, yellow. 5, 6, and then the multiplier is 4 zeros again. So 560,000 ohms or 560K. No problems there. 566, that can stay in circuit. Green, or red, red, green. So we've got 2, 2, and then the multiplier is green, so that's 5 zeros. That's 2.2 million ohms. That one's way up there. Let's see what this one reads. 2.4, no problems whatsoever. That can stay. Let's read this resistor right here. Brown, black, red. So brown, 1, black, 0, red, another 2 zeros. So 1 k ohm. So let's see how close this is. 1.18, not a problem. So you can see that slightly beyond 10%, but that's not going to make any difference if I change this out. That resistor can stay. No big deal whatsoever. Let's test this one here. So this is 151. So 150 ohms. Let's see what this one reads. Oops. Ooh, 229. That's another one that has to go. That's way off. So far this one has to go, and this one has to go. Let's test this one here that I've opened up. Really curious about that one. So this is 3, 9, and then the multiplier is 3 zeros. So 39,000 ohms or 39 k ohms. 35. That's pretty good. This one's gone the opposite way. No problems there. That can stay there. Let's see, what other one? Now, this one here, this is usually the one that always moves. It's on the rectifier tube socket. So, and this is dealing with the brunt of the load on the plate. So chances are this one is going to have moved. I can almost guarantee it. You can even see the colors changed. Yeah, 44 ohms. So this is 3, 3, and then 0. So this should be 33 ohms. This is 44 ohms. So I'll definitely change this one out. And what I'm going to do is I'm going to end up putting a metal film resistor in there. So that'll be nice and stable in this spot right here. So that's one that needs to be changed. You'll recall in the other radio that I worked on here not long ago, I replaced this as well. These ones here always move in value. They're always getting warm, right? There's another resistor down here, red, red, orange. So that's another 22k ohm resistor. Let's see what that one reads. Wow, look at that one. Almost spot on 22k ohms. No problems there. So there's one hiding under here is brown, black, green. So that's brown is 1, black is 0, and green is 5 zeros after that. So 1 million ohms. So let's see if I can get a reading on that. 1.1 meg, not a problem. That can stay. See this one here? This one is brown, black, blue. So 1, 0, and 6 zeros. So that's 10 million ohms. No problems. That's 10.9 meg. Not an issue in this circuit whatsoever. So all in all, the only resistors that really need to be changed are this one, and this one. This one I expected to go. So technically there's 2 resistors in here that are really bad. Other than that, all the rest of them are good. So I vote to leave all the resistors in just the way they are, and we'll try the receiver out and see how well it works. So I'll get on replacing both of these resistors and this one under my fingers here, and we'll try it out. The new resistors have been installed. The 390k resistor is here, the 150 ohm resistor is right here, and the new 33 ohm resistor is right here. I've cleaned the potentiometers with contact cleaner and the switch here as well. I've also lubricated the shafts here with just a little bit of oil, and I've also done that to the tuning capacitor on the upper side of the chassis, and I just wiped down the chassis and cleaned off the tubes, and the thing looks like brand new. There's basically nothing to clean on this. It's in such nice condition. So it looks like I can do the entire alignment procedure from the upper portion of the chassis. So do you think this thing is going to work? Let's try it out. So what I'm going to do is I'm just going to put the bottom pan on this. So I'll fasten the bottom pan, turn the thing over, and we'll give it a try. All right, the moment of truth has arrived. I have the bottom cover back on the radio. I've cleaned the upper portion of the chassis, and I've cleaned off all of the tubes. I've lubricated the tuning capacitor here and everything, so it's ready to try out at this point. I have this thing plugged into my isolation transformer and current limited variac supply because this is the first power up and I want to bring it up very, very slowly just in case there is something wrong. So there's no IF alignment. There is no alignment to the oscillator or to the antenna section or anything. I haven't even tested any of the tubes. So what do you think? Do you think it's going to work on its first try? Or do you think we're going to need to go back into this thing again? Well, let's find out. So I have the antenna attached to an external antenna, and I also have my test speaker attached, so I'm ready to go. So the very first thing I want to do is turn this thing on and just have it on, and then I'll use my isolation transformer and variac supply to slowly bring this thing up. So I'll turn that on right now, and I'll turn the isolation transformer up to about 40 volts, and I'll just let that sit for a moment. Now, if any of the filaments in these vacuum tubes is open, none of the tubes will light up because all of the filaments are in series, like an old Christmas light string. So, yeah, I see light, so that's a good sign. So the filaments are good in these vacuum tubes. Now, whether there's any emission, that's another thing. So far, there is no excessive current draw. So I'm going to turn it up some more to about 75 volts, and I'll let it sit there for just a moment. So far, everything is looking really good. There's no excessive current draw on the isolation transformer or current limited variac supply. I really wish I could have that in the shot here so you can see the dim bulbs glowing and everything like that, but it's just so big and all of this stuff won't fit in this shot. So I'll turn it right up now. And that's to its maximum. So now this has got full line voltage on it. And it's doing well. No problems whatsoever. And I think I might even hear some action in the speaker just a little bit. So let's see. That would be tone. Wow. Wow, no alignment or anything. Nothing has been done to this at this point, except just the components on the underside. So you can imagine what doing an alignment is going to do to this receiver. It's going to wake it right up. So doing an IF alignment and the oscillator alignment and antenna alignment looks like it can all be done from the upper portion of the chassis. So what I need to do is I need to get this all set up with some test gear, a signal generator and everything, and I'll bring you through the IF alignment with me. That's the very first alignment that needs to be done on a radio receiver. The antenna and the oscillator alignment can be done after that. We need to get the IF chain working correctly first, so that's what we'll focus on now. I'm ready to perform an IF alignment on this radio receiver, and my test equipment is set up as follows. My signal generator is set to 455 kilohertz. That's the frequency of the IF section here, and I need to peak up these adjustments here until I get maximum amplitude on the screen, and I'll show you that here in just a moment. That 455 kilohertz signal is modulated by a 1000 cycle tone or 1 kilohertz tone at 50% modulation. The output of my signal generator is about 1.3 millivolts right now, and that is being fed directly to the antenna input leads right here. This is a bit of a shortcut because the IF section in here is already working. It's working quite well, so I can cram a bit of a signal through the antenna section and align the IF just fine. Now, as I mentioned in many of my other videos, the trick behind a successful alignment in anything is to keep the device under test from seeing the test equipment. So you want to keep your test equipment invisible to the device under test. By me feeding the signal into the inputs, the antenna input section that's really far away from the IF chain, and it has to go through all of this section. And this isn't even tuned for 455. The lowest frequency on the dial is about 550 kilohertz. So I'm just pushing a signal through this section just to get it into the IF, and then I'll peak this up as much as I can. You'll notice I also have the tuning condenser fully meshed. And by having the condenser fully meshed, it's at the bottom portion of the AM broadcast band. And it's also nice and quiet there as well. I have my oscilloscope attached across the speaker leads here, and all I'm going to do is turn the volume up until I get a signal you can see on the oscilloscope screen. And now what I'm going to do is just peak up the adjustments. So what I'll do is I'll just disconnect the speaker so we don't need to listen to that. And what I'm going to do is just move these screws until I find a peak on the screen, and I just want the maximum signal I can find. So you can see just turning this just a little bit brought the amplitude up that much. So what I'll do is I'll turn this one here. Whoa, look at that. I got to turn the volume down. Just turn this down to about here, and now I'll adjust this again because it was right off the screen. Wow, look at how much gain I'm getting out of this one adjustment just by adjusting this. So turn it down again. Now I'll move the adjustment over here. And again, I'm just searching for a peak. Okay, so that was the peak and I just passed it. So if I turn past the peak, I just back the tuning tool up and search for the peak. I just want the highest amount of amplitude I can find. Now I'll go back to the first one here again. Just make sure that one's okay. Now I'll move over to this one here and I'll adjust this one, and we'll see if we can get any more amplitude out of this. This one here is pretty tight, that one. See this one here? These are very close. So again, I'm just looking for the maximum amount of amplitude, and then what I'll do is I'll go and test this one more time just to make sure that it's at the max. And sometimes this takes just a little bit of fiddling to get it right to the absolute maximum. I think that's about it right there. And that's it for the IF alignment. Now the IF chain is completely peaked up at 455 kilohertz, and I'm ready to adjust the oscillator. That's it. It's just that simple. So again, signal generator to the antenna input leads, and the oscilloscope is just across the speaker output leads. And this is how it was done in the old days a lot of the times. So again, now I need to adjust the oscillator, but in order to do that, I need to put this back into the cabinet because I need to align the pointer to the actual dial itself. And then I need to move that back and forth to adjust the oscillator so that the tracking is correct. Now, when I say tracking, what I mean is if I tune this to say 500 AM or 550 AM, it needs to point to 550 AM on the actual dial glass. If this is not calibrated correctly, it might point to 600 AM, but it's actually playing 550. So then I have to adjust this until everything tracks correctly. So 550 is pointing at 550, and then 1600 is pointing at 1600. Now, usually they have yes, they do. On the alignment sheet here, it says 600 kilohertz. So they want the bottom end aligned at 600, and they want the top end aligned at 1600 kilocycles, or 1.6 megahertz, however you want to call that. So that'll be the next step in the alignment here. Before I put the chassis back into the wooden cabinet, I want to clean the radio's dial glass, and I also want to clean that diffuser that's just below the dial glass. You know, the one with the little crack in it? We had to move that out of the way to get the needle off. Well, I completely removed that, and it just snapped into two pieces, just like that. Extremely brittle. So I thought to myself, what am I going to do to put this back together? So what I did is I put some glue on here, and then I sanded the glue on this side, and then clear coated this with a satin, but the crack still really shows up. On this side, this is the result with just the glue before sanding in any type of a satin clear coat. So looking at this plastic here has aged, and as it ages, it goes orange. And this is really common for this type of material. This type of material was used in Hallicrafters radios and things like that for their dial as well. So this is more along the lines of the color when it came out. It's actually just a little bit lighter than that. So kind of a yellowy color. And again, just because of age, it's changed color. You can really see where the light's shining. It's really gone dark orange here. And you can see on the edges where it's been shielded from the light, where it's been held in, is where it's a little bit lighter on these sides here. So I'm thinking to myself, what am I going to do to replace this thing? This is a diffuser. You know, it has to diffuse the light and everything. So I looked at different types of plastics, and I thought, maybe a thin paper diffuser or something in there would work, but nothing really worked until I thought, hey, what if I etch a piece of circuit board and then just use it as the diffuser? And there it is. And it works really nice with the light shining through it as well, and it gives it a nice golden type of color with the light shining through it. So this is the replacement diffuser for this one right here. That broke, and that's turned all orange now. So you can see here, everything's all sized up and cut just right so that it fits right in there. So there it is. The new dial diffuser. That'll be sitting right about here. Let's perform a dial alignment, an oscillator alignment, and an antenna alignment on this radio receiver. So here's how I have everything set up. I have the little door on the top open here, and as you can see, if I shut the door, the dial disappears. So I have a light set up quite a ways from the dial on the top side, and what it's doing is it's reflecting the dial glass onto that little diffuser, and that'll allow us to align this from the backside without me having to move the camera 100 times to do this alignment. So that worked out quite well. This is sitting right on top of the bench right now, and if I had to have a second camera, I'd have to have about a 10-foot tripod to get it over top and focus down on the dial. So this worked out really nice for this little radio receiver. It's kind of an awkward radio to align on camera, just the way that everything's set up. And then, of course, you have to remove the needle and everything to service the thing. So you have to align the dial in the radio itself, which is a little bit difficult in some cases. So this just happened to work out okay. So the very first thing that I've done is, you can see the needle here. I'll just zoom on in. So you can see the needle is right there. Okay, so I'll move the needle from the front side here, and you can see it moving. So what I did to align the needle here is I moved the capacitor. You can see the tuning cap right over here, completely meshed right there. So it completely meshes on that one side of the 5, on the 55, and on the other side of the dial. It's a really small tuning knob on the top here, so it takes a while to move it from end to end. That would be one improvement that they could have made to this. And as you see, that it stops right at this end of the 0 here. So what I did is I put the little needle on, and I just made it so that it moves from end to end evenly. And we'll see if we can get a dial alignment with that. That's most likely the way that they intended it, because it stops on each side of each number at one end of the dial, right? So that right there is the end. That's as far as it'll go. So what I've done is I've taken the dial string. See if I can point to this without burning myself on a blazing hot tube here. That tube is incredibly hot. So what I've done is I've taken the dial string and I've just looped it through this one loop at first. So it went through this, and then the dial string came on the outside here and then came over here. So that allows me to move the dial pointer back and forth on the dial string without cutting the dial string, and leaving this in one spot, so I can move the needle to where it needs to be on the dial. So I moved it right to this point, and then what I did is I rotate this to the other end. You see this here? I'd rotate this to the other end, and then I'd check to make sure that it's on the other side of the 0 like we saw. And I would just very gently move this back and forth until I got that into alignment. Once I had that, then I took the little string, and then I put it over this little area here, and that'll stop the actual needle from slipping on the string. So there'll be no slipping at that point now. So now this is pretty solid, and you can just leave it like this. You don't need to put any glue or anything on it. You can just leave it like that. A lot of people like to fasten this stuff with glue, and that just makes a total pain for alignment, or to get this off the next time you need to. So it's just looped through, and the tension of the string will hold the string into the pointer. So no problems there. So the very first thing that we want to do here is we want to make the dial track correctly. So what I need to do is feed the oscillator, or feed the antenna section of the radio with a 1600 kilohertz or 1.6 megahertz signal, and I need to move this dial to 1.6 megahertz. So what I'll do is I'll move this right where it's supposed to be. So you can see right here is 1400. This little notch is 1500. And then this one right here is 1600, and that'd be about right center. So what I need to do now is turn my signal generator to 1.6 megahertz or 1600 AM. So I'm just going to reach over here and do that. And as you can hear, just turn the volume up. It's close, but it's not on. So in order to adjust that, what I need to do is adjust this one setting right here. So this is the oscillator, and this is the antenna, and this will allow me to align the dial accuracy correctly so that it'll track right. So what I'm going to do is just get a screwdriver here and move this. So you see how I can move that right off frequency? And that's about as close as I'm going to get, right about there. Now this peaks the signal up. So this is the antenna section. So what I need to do now is turn this just for maximum noise, really, just till it's at its most sensitive point. You can hear it's picking up right there. You can hear it just goes away. Right about there is its most sensitive point. So now what I need to do is move the dial. You can even hear the statics picked up. There's no antenna on this, just the signal generator. You can hear it's already trying to receive. Listen, no antenna. You hear that? So you can see already it's really starting to work well. So what I want to do now is move this back down to 600. This is the other alignment point. So I need to align this at 600 AM. So right about there is going to be 600. I zoom on into that. You see it's right on top of 600 right there. So now in order to align that, I need to turn this one right here, this little one right down in here. So I'll turn my signal generator to 600. So that's 600 kilohertz. So let's see how far away that is. So you can see that's quite a ways off. Sometimes they're way over here, right? This is actually not far off. So I'll put this right on top. Right about there is the strongest. So that's right on top. So now what I'm going to do is turn this until I move the dial right on top. So you can see I can move the dial around. If I wanted to, say 600 was over here, okay? See, you can hear 600 there now. So I need to bring this to this point right here. So now I'll move this. Right there. Now I need to go back up to the upper end and make sure that the dial accuracy is correct. If not, I have to readjust again. So I'll move this back up to 1600. I'll just zoom on in here. So right about there. So I'll put my signal generator now to 1600. And it's very close. So adjust the tracking here again. It did move. And I'll adjust the sensitivity again, so the antenna adjustment here, so this will make it more sensitive. Right about there is at its max. It's very close. So now I'll move back down to 600. Right about there. Turn the signal generator to 600. Look at how close that is now. So I'll just make sure that this is spot on. Did move just a little. So when you're aligning this, you're looking for the deepest tone. That's another thing that I should explain. So when you're tuning this, you'll hear there's kind of a staticky noise, and it'll kind of, as you get onto frequency, the static will go away and the tone gets nice and deep. And that's what you're looking for. So here, I'll tune this off and I'll give you an idea here. Turn this up a little bit. Okay. See how that's kind of more, there's more static in there and how it's a lighter tone. You're looking for the deepest sound. Now we passed it. Right there is the deepest tone. And that's right on. So now we'll check the dial accuracy again at 1.6. So we'll just put that back up there. 1.6 megahertz or 1600 kilohertz if you like. So I'll turn this back up. And move over here. So we're just about there. The next little bump is 1600. Right on. No problems whatsoever. So I'll just make sure everything's peaked up. One more time. That's the deepest tone right there. And I think that's it. That was it for the dial alignment. Look at how well that aligned up. So what we'll do is we'll check the dial accuracy at other portions of the band. So I'll try 600 again. Alright, so 600 kilohertz. Back down we go. Perfect. So let's try another frequency. Okay, let's try 900. 900 kilohertz. Okay, so let's move this up to 900. Look at that dial accuracy. Spot on. Having dial accuracy like this and a radio, a lot of the times you'll align both ends and it'll be sitting here or it'll be sitting here when you want to, you know, try it right in the center, but the dial accuracy on this is just so nice. And that could be attributed to those really good capacitors too as well. So I'm using those, you know, really high quality mica capacitors where they had those other ones in there. And of course now the frequency drift of this radio receiver is going to be absolutely minimized. So it's going to be a really nice radio to listen to. And that's it. The thing is ready to listen to now at this point. So let's see how sensitive this thing is. I'll hook it up to an antenna and we'll cruise through the dial. Let's check out this radio receiver's performance. Right now it's the daytime here, so that means that we're just going to be hearing local radio stations and some flamethrower radio stations. When I say flamethrower radio stations, I mean really high-powered AM radio stations. At nighttime, lots and lots of radio stations are all over the band. So that means that there's multiple radio stations on one frequency in some cases, just because they're all coming in at the same time. And that's known as conditions, sometimes known as skip conditions. So right now, it's that time of day when basically only local radio stations and, as I say, very high-powered AM radio stations can be heard. So it'll give us a better idea of the, you know, the sound quality of this, and the band really isn't so incredibly crowded. Now, when you're looking at the band, you'll notice in some cases you'll hear radio stations that might be on either side of the notch, and that's because where the lens is. So if the lens was right in front of it, the needle would be right in front. The dial accuracy on this radio really is quite incredible. It's extremely accurate. So, you know, if I was listening to AM 600, it would be right on that mark. Yet on the camera, it might look off to one side. Again, that's just because where the lens is sitting. So I'll turn up the radio here and let's take a listen to some stations.
I'm not trying to stretch anything beyond the Bible here.
This thing has really nice sound. They did a really nice job putting the speaker system in this together. It's set back a little bit, and it looks like they have a little bit of a chamber in there. So they spent some time tuning this thing. It really does sound nice.
That much of it had been exaggerated. Like, you don't view him as a long-term piece.
I don't see for a project.
Oh, really?
So I wrote for the team that's safe and successful.
It's brilliant for tomorrow afternoon with highs.
The usage term impeachment and regret. And that home was in Seattle.
God,
Yeah.
the sky is falling, they're lighting their...
Do it right. Pan feed on ABC because
And has a larger discount. In North Shore Auto Mall.
Higher.
I just hang on a gay good for them. Is visible just
So when did you go up?
So as you can hear, it has really good receive, and the radio is working incredibly well. And again, this is just local radio stations, no nighttime radio station, no skip conditions or anything like that. And the sound quality of this thing is excellent. They really did a nice job tuning the speaker system in this, especially with that little chamber in there. So I imagine if this was sitting up against a wall or something like that, that would probably even enhance the sound. Lots of bass in the speaker. So they did a really nice job putting this thing together. And as I said before, the dial accuracy on this thing is just incredible. Very spot on. Now again, it may not have been that great. Maybe it was when it rolled right off the factory floor, it was like this with those brand new capacitors. But with those micas, I'm sure that, you know, really helped the dial accuracy. And this thing has been on for hours, and the dial drift is zip. There's no dial drift in this thing whatsoever. So very impressed with this Rogers Majestic radio. This little Chairside really turned out to be a very nice design. And now for the answer to the last video's trivia question. The question was, what is this thing? What does it do? If you're just tuning in now, you're going to want to take a look at this thing and take your best guess, because I'm going to answer this in just a moment. All right, you're going to want to pause the video right about now, or you're going to hear the answer if you're just tuning in. So those of you that answered vacuum high voltage relay, you've got it correct. This is for working up in the high kilovolt range. And the reason that they have a vacuum in here is to stop arc over and things like that. So you can see a little exhaust tip on the top. I had some people say it looks like a glass distributor. Kind of does, actually. It really does look like a glass distributor. So the piece that's missing out of the bottom is this thing. That's the coil. And I guess the person that removed this from service or had this coil at some time, it doesn't really look like there's any time on this thing, who has removed this from circuit, pulled this contact right off, and there's just a little piece of wire left. So way back when, I soldered this new lead into here, and I managed to resurrect this coil, which is kind of nice. So what I'm going to do is get a power supply set up, and I'll activate this relay. I'll be right back. Okay, so I'll slide the coil in. It's a real nice fit. Just like so. I'll turn on my high voltage power supply. This takes around 50 volts to turn this thing on. Actually, just under 50 volts. So here we go. Get a closer shot of that. So you can see that this one here is the center contact. And you can see that this would be the normally closed and this would be the normally open position. So it's a double pull, double throw relay. All completely sealed. So everything that moves is inside a vacuum or a gas-filled environment. So usually what they do is they either vacuum these things out or, again, they fill them with a gas so that they don't arc over inside. This one looks like it has a getter on the side but hasn't been flashed. And the reason that they may not have flashed that getter is because it's going to put this big spot here, and maybe it would create a path to arc through that spot. I'm really not quite sure why they didn't flash that getter. But there it is. High voltage vacuum relay. And now for the next video's trivia question. What service was this device used in? Bonus points for its actual part number. So I'd be looking for a CV number. And its frequency range. So you can see the size of this little fella is pretty small. This will plug into a crystal socket. That's how small it is. It perfectly fits one of those little ceramic crystal sockets. And some bonus trivia for the next video. We know that mica capacitors are used in oscillator circuits and circuitry that requires very high stability with temperature change. So we all know if we use just standard style capacitors in an oscillator circuit, temperature variation will cause the oscillator to move off frequency, either, high or low, depending on how the circuit is built. So capacitors are extremely important whenever you're dealing with circuits that are very accurate. And mica capacitors are one solution to keep oscillators nice and stable. And any type of a circuit that you need stability in where there's a lot of temperature movement. Here is another type of mica capacitor. This is very close to the one that I installed in that radio. They kind of look a little bit like dominoes. And I've talked about how to read these capacitors in other videos. Now, these capacitors here that I removed out of that radio, just for trivia's sake, out of that radio, what type of capacitors are these? So you can see their coating is very similar to this mica capacitor right here, but what is inside these capacitors? This one here is a really big hint. We'll take a look, we'll break one of these open in the next video, and we'll take a look inside this and see exactly what's inside, and we'll also do some measurements to see if it leaks. before we even open the thing up, the capacitor tester will tell us really what's inside this thing. Thanks for stopping by the lab today. I hope you enjoyed this video involving this Rogers Chairside radio. If you did enjoy this video, you can let me know by giving me a big thumbs up and hang around. There'll be many more videos like this coming in the near future. We'll be taking a look at vacuum tube and solid state electronics alike. So there'll be a lot of repairs, restoration, troubleshooting procedures, and electronic design on this channel. So if you haven't subscribed, now would be a good time to do that as well. If you're interested in taking your electronics knowledge to the next level and learning electronics in a very different and effective way, you're going to want to check out my ongoing electronics course on Patreon. I'll put the link just below this video's description, and I'll also pin the link right at the top of the comments section. There are a lot of videos on Patreon involving designing with circuit boards, designing with vacuum tubes, point-to-point, all sorts of very interesting things. And right now, we're building our very own customized test equipment to make troubleshooting a lot easier. So you're definitely going to want to check that out. All right, until next time, take care. Bye for now.